Welcome to this audiobook on DevSecOps, a journey into the world where development, security, and operations unite. Whether you're a developer, a system administrator, or a security professional, this book is designed to help you understand how these three worlds come together to build more secure, reliable, and scalable software. DevSecOps isn't just a buzzword or a trend. It's a mindset shift. It's about embedding security into every part of the software development lifecycle, not treating it as an afterthought or a last-minute checklist. Traditionally, development teams focused on shipping features fast, while operations teams ensured stability and uptime, and security teams stepped in at the end to run scans and fix vulnerabilities. This siloed approach often caused delays, miscommunications, and even left security gaps unnoticed until it was too late. With DevSecOps, we break down these silos. Security becomes everyone's responsibility. From the very first line of code to deployment and beyond, security practices are integrated into the process. Developers write secure code with tools that automatically check for vulnerabilities as they work. Continuous integration pipelines run automated security scans alongside unit tests. Infrastructure is treated as code, versioned and reviewed like any other software, making it easier to audit and manage securely. This book will walk you through the core principles of DevSecOps, from the cultural mindset to the practical tools. We'll explore how you can implement security automation in your C/CD pipeline, how to manage secrets and credentials safely, and how to respond to incidents in real time with confidence. You'll also learn about threat modeling, secure coding practices, compliance in cloud environments, and how to make security a collaborative effort across your organization. As we move through the chapters, the goal is not just to teach you the tools and techniques but to help you think differently about security. Security is not a gate to pass through at the end. It's a thread woven into every part of the software fabric. By the end of this audiobook, you'll be able to confidently apply DevSecOps principles to your workflows, build a culture of shared responsibility, and deliver software that's not just fast and scalable, but truly secure. So get comfortable, plug in your headphones, and let's dive into the world of DevSecOps, where speed and security go hand in hand. Let's walk through the core principles of DevSecOps, starting with the cultural mindset and flowing naturally into the practical tools that bring it all to life. And I'll keep it in a tone suitable for your audiobook. At the heart of DevSecOps lies a cultural transformation. It's not just about adopting new tools or writing more secure code, it's about changing how teams think, communicate, and collaborate. Traditionally, security was seen as the job of a separate team, often brought in late in the development cycle. This led to bottlenecks, delays, and sometimes friction between departments. DevSecOps turns that model on its head. In a DevSecOps culture, security becomes a shared responsibility. Developers, operations teams, and security professionals work together from day one. It's a culture of openness, transparency, and continuous learning. Teams communicate more frequently, align their goals, and collaborate in real time. Instead of pointing fingers when something breaks, they work together to fix the problem, and more importantly, to prevent it from happening again. Another key part of the DevSecOps mindset is shift left, the idea of addressing security earlier in the development process. That means identifying risks, scanning for vulnerabilities, and fixing issues while the software is still in development, rather than waiting until deployment or production. This not only reduces costs but also improves security and accelerates delivery. Now let's talk about automation, which is fundamental to DevSecOps. Manual processes can't keep up with the speed of modern development. Automation brings consistency, speed, and scalability. From code scanning to infrastructure provisioning, security testing to compliance checks, everything that can be automated should be. That includes things like automated code linting for security best practices, running container image scans during C builds, and automatically rotating secrets or access keys. Continuous integration and continuous deployment pipelines, or C/CD, become the highway where all this happens. Security tools are embedded directly into these pipelines, running checks as code is built, tested, and deployed. This way, vulnerabilities are caught early, before they ever reach production. If something fails a security check, the pipeline can automatically stop the deployment, alert the team, and even suggest fixes. On the tooling side, DevSecOps brings a rich ecosystem. There are static application security testing tools, known as SAST, which analyze your code for vulnerabilities without actually running it. There are dynamic tools, DAST, that test your running applications for common security flaws. There's infrastructure as code scanning, which checks your Terraform or CloudFormation files for misconfigurations that could lead to breaches. Secret scanners look for accidentally committed credentials in version control systems. Container scanners examine Docker images for known vulnerabilities before they're pushed to a registry. The list goes on, but what matters most is choosing tools that integrate smoothly with your workflow and give fast, actionable feedback. And finally, One of the most important principles is observability and response. DevSecOps doesn't stop when code is deployed. Monitoring and logging tools are used to detect threats in real time. Alerts are sent when suspicious activity is detected. Security teams, or even automated playbooks, can respond instantly, contain the threat, and begin the incident response process. It's about being proactive, not reactive. In summary, the core principles of DevSecOps blend culture, automation, and collaboration. It's about building trust between teams, embedding security early, automating wherever possible, and being ready to detect and respond to threats at any moment. When these principles come together, they create a pipeline that delivers not just software, but secure, resilient, and trustworthy software, built for the modern world. Now that we've explored the mindset and core principles of DevSecOps, let's look at the tools that support this modern approach to building secure software. These tools cover every phase of the development lifecycle, from writing code, to building and testing, to deploying and monitoring in production. Let's start with tools for static code analysis, also known as SAST tools. These analyze your source code without executing it. They look for common security issues like SQL injection vulnerabilities, hard-coded secrets, or improper use of libraries. A popular example here is SonarQube. It integrates into your C pipeline and gives developers immediate feedback on code quality and security. Another is SemGrep, which is fast, lightweight, and customizable. SAST tools are all about catching issues early, right as developers are writing the code. Next, we have dependency scanning tools. These look at the open-source packages your application depends on and check them for known vulnerabilities. Tools like Snike, Dependabat, and a WASP dependency check help keep your software safe by ensuring your libraries are up to date and free from known exploits. It's surprising how many security breaches come not from your code, but from a vulnerable package you didn't even write. Then there's DAST, or Dynamic Application Security Testing. These tools test your application while it's running. They simulate attacks like an external hacker might perform, scanning for open endpoints, injection flaws, or insecure authentication. A tool like a WASP Zap is a great example. It can be run as part of your C/CD pipeline or used interactively during testing. As more applications move into containers, container security becomes critical. Here, tools like Trivy, Grip, and Docker Scout scan your Docker images for known vulnerabilities in the base image and installed packages. Some of these tools can even suggest safer versions of the image or flag misconfigurations, like if you're running your container as root, which is a big no-no in production. Another essential piece of the puzzle is infrastructure as code scanning. Tools like Checkov, Terraform Sentinel, and TFSec analyze your infrastructure definitions, your Terraform, Kubernetes, or CloudFormation files, for security missteps. Things like OpenS3 buckets, overly permissive IAM roles, or exposed ports. Because infrastructure today is defined and managed like software, it makes sense to apply the same rigorous checks. Secrets management is another area where DevSecOps shines. Instead of hard-coding passwords, tokens, or API keys in your config files, which is a major security risk, tools like HashiCorp Vault, AWS Secrets Manager, or Doppler can store them securely. These secrets can be injected into your application only when needed and rotated automatically on a schedule or after a breach. In production, you want to know what's going on. That's where monitoring and observability tools come in. Tools like Prometheus, Grafana, Datadog, and ELK Stack help you visualize metrics, logs, and traces. But from a security perspective, you also want tools like Falco or Aqua Security that monitor runtime behavior and can alert you if something suspicious happens, like a container trying to access the host system or unexpected network traffic patterns. Finally, let's not forget about policy enforcement and compliance automation. Tools like OPA, Open Policy Agent, Kubernetes Admission Controllers, and Cloud Custodian can enforce security policies automatically, preventing misconfigured resources from being deployed, or denying access to resources that don't meet security criteria. With all these tools working together, integrated into a well-designed C/CD pipeline, DevSecOps becomes more than a philosophy. It becomes a powerful, practical framework for secure development. And while no tool can fix a broken culture, these tools, when combined with a DevSecOps mindset, help teams move faster, stay safer, and build more trustworthy systems. Let's dive into how Google implements DevSecOps practices, and we'll keep it smooth and story-like for your audiobook. When we talk about DevSecOps at scale, few companies embody it better than Google. With thousands of engineers, global infrastructure, and a constant stream of new products, Google had to develop a secure development model that works at an enormous scale. But interestingly, they didn't start by calling it DevSecOps. They started with a foundational philosophy: security by design. At Google, security is built into the very DNA of software development. Every step of the life cycle, from writing code to deploying it globally, has layers of automation, monitoring, and controls. But more importantly, Google created a culture that encourages engineers to take ownership of security, not defer it to someone else. One of the most important practices Google pioneered is the concept of zero trust architecture. This model assumes that nothing inside or outside the network can be trusted by default, not users, not services, not even devices. Access is granted based on identity, context, and policies, not on being inside a particular network. This principle drives both their internal security and cloud products like Beyond Corp. When it comes to software development, Google makes heavy use of automated security tools integrated directly into the development pipeline. Every code commit goes through rigorous testing, static code analysis, dependency checks, and policy enforcement. Google has its own internal systems that behave like SAST, DAST, and container scanning tools all rolled into one. But they also use and contribute to open source tools, like Graphies and Critus, which help define and enforce security policies for container images before they are deployed to production. Another powerful concept is binary authorization. In Google's infrastructure, code can only be deployed if it has been verified and signed at every stage, from source to build to deploy. This ensures that what's running in production is exactly what was tested and approved. Nothing goes live without traceability. And then there's Site Reliability Engineering, or SRE. While it's not purely a security role, Google's SRE teams are deeply involved in ensuring the reliability, availability, and security of systems. They monitor for anomalies, respond to incidents, and write postmortems, not to assign blame, but to improve processes. Security incidents are treated with the same rigor as system outages, and lessons learned are fed back into engineering practices. On the infrastructure side, Google treats infrastructure as code with strong governance. Kubernetes, originally developed at Google, plays a huge role in enabling consistent, secure deployment practices. Policies can be enforced at the cluster level, using tools like OPA Gatekeeper, to ensure only compliant workloads are deployed. Secrets management is handled centrally, and access is strictly controlled through fine-grained IAM. Education is also a big part of their DevSecOps practice. Google engineers undergo regular security training, and there are internal security champions embedded in teams. These aren't gatekeepers, they're enablers, helping their teams build safer software without slowing them down. And finally, Google's approach to vulnerability response is worth noting. They run one of the most respected vulnerability reward programs in the world, offering rewards for researchers who find bugs in Google services. Internally, any vulnerability is tracked, prioritized, and fixed within strict timeframes, known as bug bars, which define how quickly issues must be remediated based on severity. So what can we take away from Google's example? DevSecOps at Google is not a single tool or process. It's an ecosystem, a combination of automation, cultural values, and a commitment to doing things securely from the start. Their success lies in making security a natural part of development, not a speed bump. For smaller teams and companies, the lesson is clear. Start small, but think big. You may not need Google's infrastructure, but you can adopt the mindset, build secure by default, automate where you can, and make security everyone's job. Chapter: Red Hat Enterprise Linux. RHEL. Welcome to this chapter on Red Hat Enterprise Linux, or simply RHEL. RHEL is one of the most widely used Linux distributions in the enterprise world. It is known for its reliability, security, and support, making it a go-to choice for businesses and organizations running mission-critical applications. In this chapter, we'll explore 3 key aspects of working with RHEL: configuring and managing the operating system, writing bash scripts for automation, and managing disk storage using LVM, or Logical Volume Manager. Section 1. Configuring and managing the operating system. When working with RHEL, system configuration is your foundation. The operating system is typically managed through both the graphical interface and the command line. But in enterprise environments, the command line is king. Let's talk about some of the fundamental tasks. User management. You create users using the user_add command and set passwords with password. Managing user groups with group_add, usermod, and gpassword helps control access to files and services. Service management with systemd. RHEL uses systemd to manage services. For example, systemctl start httpd starts the Apache web server. Use systemctl enable to start a service at boot. Always check the status with systemctl status. Network configuration. RHEL uses the nmcli command to manage network interfaces. You can set IP addresses, DNS servers, and even manage wireless connections with this tool. Software installation. Software is managed using the DNF package manager. Want to install a package? Just type DNF install. You can also update your entire system using dnfupdate.se Linux. Security Enhanced Linux, or SE Linux, is built into RAL. It enforces security policies and restricts processes. You can check its status with sysstatus, and temporarily set it to permissive mode using ctn40. Section 2. Bash Scripting. Let's move into Bash Scripting, your secret weapon for automation. A bash script is just a series of commands saved in a file. The magic begins with the shebang line at the top. !bin/bash. From there, you can do things like create loops and conditionals, such as for loops and if statements. Pass and use variables, like username equals $1, to accept arguments from the command line. Schedule your scripts with cron jobs, using cron tab e. Here's a simple example. !bin/bash. Echo starting backup. tar czf/backup/home.tar.g/home. Echo backup complete. Scripts like these are great for backups, maintenance, and repeating daily tasks. Section 3. Disk Management with LVM. Now, let's dive into LVM, Logical Volume Manager. This is one of RAL's most powerful features for disk and storage management. With LVM, you're not stuck with fixed-size partitions. You can create volume groups and then split them into flexible logical volumes. Here's how it works, step by step. Create physical volumes using bvcreate. Combine them into a volume group using vgcreate. Carve out logical volumes using lvfcreate. For example, bvcreate/dev/sdb. avgcreate miv/dev/sdb. lvacreate l10gn mvolume mivga. You now have a 10 GB logical volume named mvolume. Format it with mkfs.ext4, mount it, and it's ready to go. What makes LVM especially useful is resizing. You can extend a volume on the fly using lextend, and even reduce one if necessary. Chapter: IP Networking and Network Security. Welcome to this in-depth look at IP networking and network security, the critical infrastructure that underpins all modern computing. Whether you're managing enterprise systems or configuring home labs, understanding how networks operate and how to secure them is essential. Let's begin with network protocols. These protocols govern the format and transmission of data across networks. At the heart of all internet and intranet communication is the TCP/IP model, which consists of 4 layers: the link layer, the internet layer, the transport layer, and the application layer. The Internet Protocol, IP, handles addressing and routing. Each device on a network is assigned a unique IP address. IPv4, still the most widely used version, uses 32-bit addresses, allowing roughly 4.3 billion unique devices. IPv6, its successor, uses 128-bit addresses, vastly expanding the address space and solving the shortage issue. TCP, or Transmission Control Protocol, ensures reliable ordered delivery of a stream of bytes. It uses a 3-way handshake to establish a connection and guarantees data delivery with acknowledgements and retransmissions. In contrast, UDP, or User Datagram Protocol, sacrifices reliability for speed, making it ideal for real-time applications like video streaming and DNS queries. Moving higher in the stack, we find protocols like HTTP and HTTPS, which are the basis of web traffic. HTTPS uses TLS, Transport Layer Security, to encrypt communication between client and server. Email relies on SMTP to send messages, IMAP or POP3 to retrieve them, while DNS resolves domain names like example.com into IP addresses. Next, we step into the world of routing and subnetting. Routing is performed by devices such as routers, which use routing tables to determine the best path for packet delivery. Routes can be static, where the path is manually set, or dynamic, where protocols like OSPF, Open Shortest Path First, and BGP, Border Gateway Protocol, adjust routes based on network changes. Subnetting allows a large IP network to be broken into smaller, logical segments. For example, the IP address 192.168.1.024 denotes a subnet where 256 addresses are available, from 192.168.1.0 to 192.168.1.255. This division reduces broadcast traffic, improves security by isolating devices, and allows for more organized network management. Using CIDR, classless interdomain routing, notation, subnetting becomes more flexible than the older class-based system. To calculate a subnet, you need to understand the subnet mask. A /24 mask, or 255.255.255.0, allows 254 usable host addresses. A /26 mask, or 255.255.255.192, only allows 62. Tools like IPCalc or subnet calculators can help automate these calculations. Now let's move into network security, starting with firewalls. A firewall is a security system that monitors and controls incoming and outgoing network traffic based on predetermined rules. In Linux, the most commonly used firewall is iptables, or its successor, ftables. These tools allow administrators to drop or accept packets based on criteria like source and destination IP, port number, or protocol. Modern firewalls may be stateful, meaning they track connections over time, and application-aware, meaning they inspect application data and not just packet headers. Enterprise networks often use next-generation firewalls, NGFWs, that include features like deep packet inspection, intrusion detection, and integration with directory services. Proxies serve both as performance enhancers and security layers. A forward proxy acts on behalf of clients, requesting resources on their behalf. This is useful for caching, content filtering, and hiding internal IP addresses. A reverse proxy, on the other hand, sits in front of web servers, forwarding client requests. It's commonly used for load balancing, SSL termination, and DDoS protection. Tools like Squid, HAProxy, and Ginx can function as both forward and reverse proxies. In some environments, you'll encounter network address translation, NAT, which allows multiple devices to share a single public IP address. This is common in home networks and helps conserve address space. Port forwarding, a form of NAT, maps traffic from specific ports on a public IP to a service running on an internal device, often used for SSH, web, or game servers. Lastly, no discussion of networking is complete without monitoring and diagnostics. Tools like ping, traceroute, netstat, SS, and cpdump help diagnose connectivity issues. For example, ping checks if a host is reachable. Traceroute maps the path to a destination. TTPdump captures packets for in-depth traffic analysis. Chapter: Automation and Configuration as Code, Ansible. Welcome to this chapter on automation, the secret weapon of efficient, scalable IT operations. In today's world, system administrators and DevOps engineers are expected to manage hundreds or even thousands of systems. Manual configuration just doesn't scale. This is where configuration as code and tools like Ansible come in. Configuration as code, often abbreviated CAC, is the practice of managing and provisioning infrastructure using machine-readable files rather than manual processes. Instead of clicking through menus or typing one-off commands, you define system configurations in a text file, version it like code, and apply it automatically to your infrastructure. Ansible is one of the most popular tools in this space. Developed by Red Hat, Ansible is open source, agentless, and extremely simple to get started with, all while being powerful enough to manage complex deployments. It uses YAML to define configurations, and connects over SSH, meaning you don't need to install a client or agent on the target systems. Let's talk about how Ansible works. At its core, Ansible operates using something called a playbook. A playbook is a YAML file that defines a set of tasks, each task representing a single unit of work, such as installing a package, creating a user, modifying a configuration file, or restarting a service. Here's what a very simple playbook looks like. Name: install Apache on a web server. Hosts: web servers. Become: true. Tasks: name: install Apache. Yum. Name: HTTPD. State: present. Name: ensure Apache is running. Service: name: HTTPD. State: started. Enabled: true. In this example, Ansible targets all hosts in the web servers group. It installs the Apache HTTP server using the Yum package manager and ensures the service is running and enabled on boot. The become: true directive means the commands will be executed with elevated privileges, usually as root. Ansible uses an inventory file to define which systems to manage. Inventories can be static, a simple list of IP addresses or hostnames, or dynamic, pulling live information from cloud providers like AWS, Azure, or GCP. Tasks in Ansible are executed using modules. Modules are reusable units of work, like Yum for package management, Copy for transferring files, Template for generating configs from Jinja 2 templates, or User for managing system accounts. You can even write your own custom modules if needed. One of Ansible's superpowers is idempotence. This means that you can run the same playbook multiple times and it will only make changes if something is out of place. If a package is already installed, Ansible won't reinstall it. If a service is already running, Ansible will move on without restarting it. Ansible also supports variables, conditionals, loops, and roles. Roles allow you to organize your configuration logic into reusable, modular pieces. For example, you can have a web server role that sets up Apache, configures firewall rules, and deploys web content, all neatly packaged for reuse. Here's an example of using a variable. Name. Create a user with a custom shell. Hosts, all. Vars. Username, Devops. Shell, /bin/bash. Tasks. Name, add user. User. Name, username, shell. This makes it easy to customize configurations for different environments or systems. Just pass in a different variable file. Security is also a consideration. Ansible provides Vault, which encrypts sensitive data like passwords and API keys. With Vault, you can keep secrets in your playbooks without exposing them in plain text. One of the best parts about Ansible is how seamlessly it integrates with C/CD pipelines. You can trigger Ansible playbooks automatically when new code is deployed, or as part of a nightly infrastructure audit. Whether you're managing a few cloud VMs or orchestrating a hybrid data center, Ansible scales with you. In real-world production environments, you'll often see Ansible paired with Git for version control, Jenkins or GitLab C for automation, and monitoring tools like Prometheus or Nagios to complete the Devops toolchain. To summarize, Ansible turns complex infrastructure management into repeatable, predictable automation. By defining system configurations in plain YAML files, you eliminate drift, reduce errors, and gain full visibility into how your environment is set up. Chapter: ITIL-compliant change management and vulnerability management. Welcome to this chapter where we dive into two critical practices in enterprise IT operations: ITIL-compliant change management and vulnerability management. These aren't just checkboxes in compliance reports. They're frameworks and processes that help organizations maintain stability while improving systems and keeping security threats at bay. Let's start with change management within the ITIL framework. The ITIL, or Information Technology Infrastructure Library, is a globally recognized set of best practices for delivering high-quality IT services. Among its many disciplines, change management stands out as one of the most important. Its primary purpose is to ensure that changes to IT systems are made in a controlled and coordinated manner. The goal is to minimize the risk of disruption to services, while still allowing the business to evolve and innovate. In an ITIL environment, a change can be anything from updating server software, rolling out new features, patching systems, replacing network components, or migrating workloads to the cloud. Each change is initiated by a request for change, or RFC. The RFC captures the details of the proposed change: what will be changed, why the change is needed, who is responsible, the timeline, the potential risks, and the rollback plan. Once submitted, the RFC is reviewed in a formal process. Depending on its risk level, the change might be classified as standard, normal, or emergency. Standard changes are routine and low risk, such as applying scheduled patches. Normal changes go through a formal assessment and approval process, often reviewed by a Change Advisory Board, or CAB. Emergency changes are fast-tracked and typically reserved for critical incidents, like patching a zero-day vulnerability in a production system. Every step of the change process is documented. This includes testing in staging environments, implementation plans, communication with stakeholders, and post-implementation reviews. Tools like ServiceNow, Jira Service Management, or BMC Remedy are commonly used to manage this lifecycle. This documentation not only supports compliance and auditing but also provides a clear history of changes for troubleshooting and improvement. Now, let's connect this to vulnerability management, another crucial layer of IT operations and security. Vulnerability management is the process of identifying, evaluating, treating, and reporting on security vulnerabilities in systems and software. The goal is to reduce an organization's exposure to threats by addressing weaknesses before they can be exploited. This process begins with discovery, scanning systems and software to detect known vulnerabilities. Tools like Qualys, Nessus, and Rapid7 are widely used for this purpose. They maintain regularly updated vulnerability databases and scan endpoints, servers, network devices, containers, and even cloud resources. A typical scan can reveal outdated software versions, missing patches, misconfigurations, and more. Once vulnerabilities are identified, the next step is prioritization. Not all vulnerabilities are equal. Some might have little to no impact, while others can allow remote code execution. The CVSS score, or Common Vulnerability Scoring System, is a standard way to assess the severity of a vulnerability. You'll also consider exploitability, asset importance, and business context. From here, the focus shifts to remediation or mitigation. Remediation involves directly fixing the vulnerability, for example, by applying a software patch. Mitigation may involve workarounds or additional controls that reduce the risk, such as disabling a vulnerable feature or adding firewall rules. If a change is needed to fix a vulnerability, it goes right back through the idle change management process, which means documenting the fix, scheduling downtime if needed, performing testing, and implementing it with appropriate approvals. Monitoring and reporting are ongoing activities. Regular reports track vulnerability trends, demonstrate progress, and support audits. Mature organizations may tie vulnerability data into their SIEM systems, like Splunk or Microsoft Sentinel, to correlate vulnerabilities with real-time threat activity. An effective vulnerability management process is proactive. It integrates with patch management, change control, and threat intelligence. It's not a one-time effort. It's continuous, evolving, and tightly coupled with IT governance. To wrap up this chapter, let's bring the two threads together. Change management ensures that IT modifications are deliberate, approved, and reversible. Vulnerability management ensures that security weaknesses are identified and addressed before they can be exploited. Together, these practices create a loop of safety and agility, allowing organizations to move fast while staying secure. They empower IT teams to take calculated action and defend their infrastructure with discipline, clarity, and precision. In the next chapter, we'll take this further by discussing incident response planning and disaster recovery strategies. Stay with us as we continue building your IT operations mastery. Chapter: Incident Response, Planning and Disaster Recovery Strategies. In this chapter, we turn our attention to the moment no organization ever wants to face, when something goes wrong. It might be a ransomware attack, a cloud outage, a misconfigured firewall, or a database crash. When the unexpected happens, incident response and disaster recovery are what stand between temporary disruption and catastrophic failure. Let's begin with incident response planning. Incident response is a structured approach to detecting, analyzing, and responding to security incidents. The objective is to minimize damage, reduce recovery time, and learn from the event to prevent future occurrences. A good incident response plan doesn't start when the incident occurs. It starts long before that, with preparation. Preparation involves defining roles and responsibilities. Who's on the incident response team? Who communicates with stakeholders and possibly law enforcement? What systems are considered high-value targets? Are the logging and monitoring tools configured to detect threats? Next is detection and analysis. You can't respond to what you don't see. This is where SIEM systems like Google Chronicle, AWS GuardDuty, and Azure Sentinel come into play. These platforms aggregate logs, detect anomalies, and generate alerts when suspicious activity is identified. Once an incident is confirmed, the focus shifts to containment. The goal is to stop the bleeding, isolate affected systems, change credentials, block malicious IP addresses. Then comes eradication, where the root cause is removed. This may involve wiping malware, patching vulnerabilities, or replacing compromised systems. After the threat is removed, the recovery phase begins. Systems are restored, services are brought back online, and access is carefully re-enabled. Finally, the post-incident review analyzes what happened, what worked, what didn't, and what needs to be improved in the plan. Cloud providers offer powerful tools to support every stage of this process. In GCP, you can use cloud logging, cloud monitoring, and Security Command Center to detect threats. Chronicle SIEM gives visibility across your enterprise. You can also define playbooks using cloud functions or workflows to automate incident response tasks. In AWS, CloudTrail records account activity, CloudWatch monitors performance and behavior, and AWS Config keeps track of changes. AWS GuardDuty detects anomalies, and AWS Systems Manager can be used to quarantine and remediate systems. In Azure, the Microsoft Sentinel SIEM offers advanced analytics and threat detection. Azure Defender provides protection for cloud resources, and Azure Logic Apps can automate responses, like isolating a virtual machine or disabling a user account after suspicious login activity. Now let's transition into disaster recovery, often abbreviated as DOCR. Disaster recovery is the strategy and process for restoring critical IT systems after a catastrophic event, whether it's a cyber attack, a natural disaster, or a massive system failure. While incident response deals with the attack in progress, disaster recovery is about resilience and restoration. A good disaster recovery strategy begins with a business impact analysis, identifying which systems are most critical, how much downtime is acceptable, and how much data loss can be tolerated. These two key metrics are known as the Recovery Time Objective, RTO, and Recovery Point Objective, RPO. The RTO defines how quickly a system must be restored. The RPO defines how much data you can afford to lose. For example, a payment processing system might have an RTO of 15 minutes and an RPO of 0, meaning no data loss is acceptable. Disaster recovery plans typically include backups, regular, verifiable, and secure copies of data. Redundancy, running systems across multiple availability zones or regions. Failover strategies, automatically switching to a backup system when the primary fails. Runbooks and automation, detailed procedures for how to bring systems back online. In the cloud, Docker becomes more flexible and more powerful. In GCP, you can leverage cloud storage for multi-regional backups, compute engine snapshots, and Cloud SQL backups. Cloud load balancing and global DNS make failover easier. You can automate DR with Deployment Manager and Infrastructure as Code templates. In AWS, services like AWS Backup, Elastic Disaster Recovery, and S3 cross-region replication are vital. You can replicate databases using RDS read replicas, and Route 53 health checks can shift traffic to healthy endpoints during outages. In Azure, tools like Azure Backup, Site Recovery, and Geo-Redundant Storage, GRS, keep your data safe across regions. With availability sets and availability zones, you build high-resilience architectures. For mission-critical services, zone-redundant databases and load balancer failover rules are essential. One often overlooked part of DR planning is testing. A plan that's never tested is just a theory. Cloud providers allow staging environments where you can simulate failover, restore from backup, and validate application functionality, all without disrupting production. To wrap this up, incident response and disaster recovery are not just checklists, they're living, breathing parts of a mature IT environment. A well-prepared organization is one that anticipates threats, practices recovery, and treats uptime and data integrity as sacred. Whether you're using GCP, AWS, or Azure, the tools are there, but strategy, discipline, and readiness are what make the difference.